This essential derivation is once again related to projectile motion. What I'll be doing is devising an equation that I can use to help me solve sophisticated projectile motion problems. It's not an equation that I need. I can go on with the standard set of equations. However, it's useful when solving more sophisticated problems to have an equation that cuts out all of the intermediate calculations. By doing a little bit of work ahead of time, I save myself some work going forward. Also, in this derivation, I'll be able to prove an aspect of projectile motion that we all recognize to be true, but in some ways this derivation stands as proof of it. What I'm going to do is begin with the very, very common projectile motion equation that I use for describing the y position of a projectile. So I'll start with that y position. Y is equal to the initial y position plus the initial y velocity multiplied by time minus 1/2 the acceleration due to gravity, and that's why the minus sign appears here, because if I choose upward to be the positive direction of my coordinate system, then the acceleration due to gravity is negative, multiplied by the time squared. That's a basic equation that I might be using to solve a projectile motion equation. What I'm going to do is make a few substitutions. What I always do when I'm doing a derivation is I take one true thing and smash it together with another true thing. So for example, the initial component of the vertical velocity, that is the initial y component of velocity, is a component of the initial velocity. As it happens, it's the sine component of the initial velocity. So I'm going to be replacing v naught y here with v naught times the sine of theta. It's also true in projectile motion that the horizontal position is equal to the initial horizontal position plus the x component of the velocity multiplied by time. We know it's one of the characteristics of projectile motion that the x component of velocity, which is v naught times the cosine of theta, never changes during projectile motion. And that's because there is no horizontal component of acceleration in the case where I'm ignoring viscous drag. So here for Vx, I'm going to be replacing that with V naught cosine theta, and I'm going to solve it around for t. So with a little bit of algebra, my process is going to be to subtract the x naught over to the left-hand side, and then to divide that whole works by V naught times the cosine of theta. So now I have these two replacements that I can make. I can replace V naught y with V naught sine theta, and I can replace t with x minus x naught over V naught cosine theta. But along the way, I'm going to make two very harmless assumptions. That doesn't even look like the word assumptions. I'm going to make two very harmless assumptions. One is that y naught is equal to 0. Right? So the initial y position I'll set equal to 0. And also that x naught is equal to 0. These are harmless choices because at the beginning of a projectile motion problem, I choose my coordinate system. So I always have the luxury of choosing the initial horizontal and vertical position to be 0. I have to have a care, though. When I finally get my result equation out of this, I have to appreciate the fact when I'm using it that I've made those initial assumptions. So here I go, making the substitution into my original projectile motion equation, that is y, the final y position, is equal to v naught y is equal to 0. So I'm going to go ahead and leave it out of the equation here. Now, I'm sorry, y naught is equal to 0. V naught y is equal to v naught sine theta. So I'm going to go ahead and write in here v naught times the sine of theta, and that needs to be multiplied by t. But I've learned that t is x divided by v naught cosine theta. So here in the denominator of v naught times the cosine of theta appears, and then that is multiplied by x. Moving on in my equation to this last bit here, I have minus 1/2 g multiplied by t squared. I'm going to make it easy on myself and just go ahead and drop in what I know t to be equal to, x divided by v naught times the cosine of theta, and square that. And I'm done, except that this equation can have a little bit of cleanup done to it to make it a little bit more compact and concise, and it'll actually reveal a little something to me in the end of my derivation here. I'll notice right here in the first term that the v naught divided by v naught cancels, so the v naught's gone. I also then recognize that sine theta divided by cosine theta is equal to the tangent of theta. So for my final result, I'm going to write y is equal to the tangent of theta multiplied by x. I suppose I should have some parentheses here. What the heck, I'll drop them in. To make sure that I realize that this x is not in the tangent itself. It is the tangent of the angle multiplied by x minus, and just rewriting this in a pleasing way, I'll take g, which appears in the numerator, and divide it by 2 times v naught squared times the cosine squared of theta. And really important not to forget, and there I also have an x, which is squared. And so here I have my final result, which is an equation that I like to refer to as the trajectory equation. The reason why is that inspection of this shows me that if I make a graph of the vertical position of a projectile as a function of the horizontal position of the projectile, it is parabolic, because you see here the x squared, and again x here in the equation. It's the equation of a parabola. And what the tangent theta and the g over 2 v naught squared cosine squared theta do is they determine the shape of that parabola as the projectile makes its way through space. This equation has great utility when I want to know the final vertical position and I don't want to mess around with time. Notice that time is not in the equation at all. Very often I can use this equation to solve a projectile motion problem in one step, whereas a great many steps and a little bit of algebra are required along the way. So this is an equation that has some utility for solving problems and also demonstrates that the motion of a projectile in the absence of the viscous drag of air is a parabola.